Welcome to the Crazy Hat Chemist. So another video in intermolecular forces. Bam! So today we're talking about the intermolecular forces in the hydrogen bond. Oh, so very important for chemistry, but even more important for biology. So here we go. It's a special case of a dipole-dipole interaction involving a polar HX bond. Okay? Hydrogen bonding is stronger when the X, that this particular element, is either a nitrogen, oxygen, or fluorine. It's strongest when it's one of those three elements. It can be other elements, but that's when it is the strongest. This results in molecules with the higher than predicted boiling points, among other physical and chemical characteristics as well. So we're going to be talking about a number of those a little bit later. The hydrogen bond in water, an intermolecular force, is about 20 kilojoules per mole, compared to an OH intra-covalent bond, which is about 460 kilojoules per mole. So you should see that the hydrogen bond is very weak compared to the intramolecular covalent bond of a hydrogen-oxygen bond. Much stronger, okay? But that's okay. All right, so there's two water molecules, and the bond between the two water molecules is a hydrogen bond. Again, it's a special case of a dipole-dipole interaction. Okay, that is that the positive end of the hydrogen and the negative end of the oxygen on two different molecules. That's why it's between molecules. It's an intermolecular force. Okay, so here's thymine and adenine, a biological example here. Right here is a hydrogen bond between a nitrogen, which is blue, and the hydrogen, which is white. Okay, the hydrogen has a delta positive charge, and the nitrogen has a delta negative charge. There's a hydrogen bond in between the two. In addition to that, there's a second hydrogen bond between thymine and adenine, and that's between the positive end of this positive end of the hydrogen on one molecule, and then the delta negative end on the oxygen on the other molecule. Okay, again, this is a dipole-dipole interaction. It's between molecules. Notice that there are two hydrogen bonds between the thymine and the adenine. Now I'm going to take another example with a biological example, and that's with cytosine and guanine. And this is a hydrogen bond right here between an oxygen, which is a delta negative, and its respective hydrogen, which is on another molecule, which is on the cytosine, as a delta positive. Okay, here's another hydrogen bond. The hydrogen bonds are in the purple there. Okay, the hydrogen bond is between the hydrogen, which is partially positive, and the nitrogen, partially negative. And another hydrogen bond. That makes a 3 hydrogen bonds for the cytosine guanine. And this hydrogen bond is between this negative, delta negative oxygen and this delta positive hydrogen right here. Okay, so one thing that you should note is that if you were to look at a DNA molecule, they are held together. The two strands, the anti-parallel strands, are held together by these hydrogen bonds internally. The more GC content, that is the more guanine cytosine content, that higher melting point of that DNA. Why? Because there are 3 hydrogen bonds in guanine and cytosine compared to the 2 in the thymine and the adenine. Okay, so here is another hydrogen bond example. This is between a water molecule and ethanol. Okay, and this is the hydrogen bond between the water molecule of the delta negative end of the oxygen on the water and the hydrogen on the ethanol molecule. Okay, and those are denoted right there like that. All right. So another example here, continuing with hydrogen bonds because it's so very important. Okay, ice, which is solid water, is an open cage structure composed of a 6-membered hexagonal rings, which accounts for its crystalline structure and its low density, i.e. it's increased in volume, that's why it's low in density. Ice is approximately 10% less dense than that of liquid water, and that's why ice floats. This is a very unusual characteristic because almost everything, as you decrease the temperature, it becomes more compact and more dense. At a certain temperature, the freezing point of water, actually at 4 degrees, That makes water expand and maximize the number of hydrogen bonds. That increases the volume and decreases the density. Therefore, ice expands and floats. Okay, so here is water molecules, and you should see that there are 6 water molecules here forming this hexagonal 6-membered ring. I'm going to point out the hydrogen bonds. Here we go. 1, 2, 3, 4, 5, and 6 hydrogen bonds. Okay, that forms this hexagonal crystalline structure. Okay, these are all between delta negative, delta positive charges on different molecules. Okay, this forms that hexagonal structure. You can see that diagrammatic blue hexagonal structure. Okay, this is looking at ice from the top, and you need to look at this as there are ice is forming this hexagonal structure with different rings as you keep on going down into it. And this is ice from the side. You still see that hexagonal structure. It's a repeating pattern. Okay, now I want you to look at liquid water. Now look at liquid water and see how compact liquid water is. Liquid water has no repeating pattern and is compact compared to ice, which has a regular repeating crystalline structure. Okay, so ice maximizes the number of hydrogen bonds at 4 hydrogen bonds per water molecule, whereas liquid water has far fewer. That is, far fewer hydrogen bonds, between 2 and 3 hydrogen bonds per water molecule. And of course, gaseous water in the gaseous state has how many hydrogen bonds? 0, because it's in the gaseous state and it's not interacting with other molecules. Okay, here's some hydrogen bonds in ice. Okay, so it's showing this repeating pattern over and over again. Okay, so there's a water molecule, and this is that hexagonal crystalline structure that I've denoted by this black circle. You should see that there's another layer right below of that same crystalline hexagonal structure. Okay, you need to think about this, and it's a 3-dimensional structure here. So either on the side or down below or up above. Same repeating pattern. There are some unique properties of water based on the strength of the hydrogen bond and the polarity of the water molecule. So one of them is the high specific heat capacity of water. In fact, water's high specific heat capacity accounts for so many things. That value is 4.184 joules per gram degrees Celsius. That is super high, and that's why it takes so much energy to do so many things dealing with water. It's the reason why water is used to put out fires. It's the reason why lakes and oceans control relative climate in the region. It's the reason why thunderstorms have huge quantities of energy associated with them. The boiling point of water, i.e. the low vapor pressure of water, is at 100 degrees Celsius, and this is exceedingly high for such a low molar mass molecule at 18 grams per mole. And you can see from this graphic, this chart right here, I've circled out water, and it is much, much higher than anything within the same group or period comparison on the periodic table. It is far, far higher in boiling point. And the reason is because water it's the second electronegative element. That is, the oxygen is the second most electronegative element, and it is polar covalently bound to that hydrogen, and there are a lot of lone pairs of electrons on that oxygen. 2 sets of lone pairs of electrons. It yields to an asymmetric molecule, and it forms a very strong hydrogen bonds between other water molecules. There's a high heat of vaporization. That high heat of vaporization is at 40.8 kilojoules per mole. This is an extremely high value. Water is a polar solvent. It will allow other polar molecules to go into water due to its polarity, its asymmetry. Okay, there are cohesive properties, cohesive forces, that is attraction of similar molecules, and adhesive properties, that is attraction of dissimilar molecules, and this forms surface tension. Okay, you can see these water striders are on the surface of water. These water striders are on the surface because there's a high amount of surface tension with water. This forms water droplets which are spherical in nature because they love themselves and they don't like other things. Okay? It's the reason why when you are a high diver, there's a stream of water that goes into the pool to disrupt some of the hydrogen bonds so that when you do dive into the water, it doesn't hurt so much. Solid water or ice is less dense than that of liquid water. That is also a result of hydrogen bonding, and you can see that in this picture right here. Okay? Water expands, and that is the reason why we cover our pipes for the winter time, depending on where you live. If you live anywhere where it gets below freezing, that water in those pipes will expand, maximize those number of hydrogen bonds, and burst those pipes. It doesn't matter even if they're metal, copper like this one here. Okay? And water is a liquid on our planet, and that is just an amazing thing. Okay? It's a liquid because the high degree of hydrogen bonds within the adjacent water molecules having those intermolecular forces. Okay? So here is a central water molecule, and I've pointed out the 4 hydrogen bonds. These are relatively weak, but they're a special case of a dipole-dipole interaction. So I want to compare this to a covalent bond. Okay? Covalent bonds are very strong, just like this praying mantis is very strong. In relationship to this ant, okay, hydrogen bonds are relatively and individually weak. So this ant, compared to that praying mantis, the ant is very weak. That praying mantis is very, very strong. However, being that that ant is an individual hydrogen bond and relatively weak, if you have large numbers of those ants, they will certainly take down that praying mantis. So in large numbers, even that weak hydrogen bond, as that intermolecular force, is strong in sum total. So think about a cup of water where there are billions and billions and billions of water molecules, if I may take something from Carl Sagan. And the sum total of those hydrogen bonds amounts to a huge amount of energy. Okay? So water can maximally bind 4 other hydrogen water molecules, and that will form 4 other hydrogen bonds, and that will be ice. Anything less than that is liquid. That is another crazy hat video, and that was all about the hydrogen bond, and I love this one. Give me a thumbs up if you like that video. Subscribe to my channel, my YouTube channel, and try to figure out what that little creature is on top of here. All right, have a great day, and I'll see you next time. Bye now.